Welcome to Module 5. So this week we will be studying logistic regression. So up until now, we have created regression models for quantitative response variables. And in creating those models, we considered predictors that were factors or that were quantitative. Okay, so but we did not consider the case where the response variable, for example, is qualitative, specifically if it's like a binary variable like a 0 or 1. So that's the idea behind logistic regression, where we will model a variable that is binary, can take 0 or 1 value, or it could take like a yes or no kind of value as well. And this is actually extensively used, okay, in the industry. The regression modeling in itself is a big part of predictive analytics, but logistic regression is extremely important. And I think that you are very much likely to encounter this in your careers if you pursue a career where you use predictive modeling. So this week we will work with a new data set. And so let's just go through the scenario in step one. So we are a risk analyst working for a credit card company, and we have access to a set of historical data that can be used to study relationships between customer characteristics and whether or not they are likely to default on their credit. So clearly now you can see that this statement here, that whether or not the customers are likely to default or not. So the default, um, uh, being default is going to be a binary variable, okay? And you will see in the table here, we have the default variable, and 0 means that the person did not default, and 1 means that they defaulted, okay? So that would be a binary variable that we're going to um, model using logistic regression. And here are various predictors. So for example, age of the individual, sex of the individual, highest education level, is the individual married or not. So that's a predictor, but it's a binary predictor. Assets, missed payments, so previously missed payments, and credit utilization. So these are all different predictors that can be used to model the response variable default. So let's look at the first step. So in the first step, we're going to first install two libraries that we're going to use in this assignment prep. So just think of them as new libraries that we're going to install each time we run step one. And once they're installed, we will be able to use them in the upcoming steps. Okay, and then so this step is pretty much the same as what we have been studying. This is where the data is read into a, a data variable, a data frame, and it's read from a CSV file. Okay, and so here are some factor variables. Okay, so we're converting variables that are read from the CSV into factors, and then we're going to print the um, first few rows of the data set to see what it looks like. So here it is. So you can see we're printing the first 6 rows of the data set, and these are the different variables. And you can see that under the variable names, we have information on what kind of variable we have. So here, for example, age is an integer, and all these other variables are factors. Credit utilization is a double variable, and what that means is it's able to take um, decimal point values. And then we have our response variable default, that is a factor. Okay, so let's now see in step two how we can create a logistic regression model for defaulting on a loan. So step two is where we will create the logistic regression model for defaulting on credit. So that is our response variable, and it takes values of 0 or 1, 1 means having defaulted on credit, and 0 means did not default on credit. And the predictors are education and credit utilization. So credit utilization is a quantitative variable. Okay, and what that means is if you have, say, $10,000 of credit available, then how much of that credit are you using? The more credit you use, the probability of defaulting on that credit becomes higher, okay, because you're using too much of the credit that is available to you. And then education, so if you notice here, it says a higher level of education is expected to be correlated with higher salary and therefore a lower risk of defaulting. So if your salary is higher and you're using your credit, whatever that is available to you, chances are that if your salary is higher, that you'll be able to make payments on that credit. So, being defaulting on that credit, the probability is lower. Okay. Now, one thing to note here, credit utilization again is a quantitative predictor, so we can just use that as is. However, qualitative education is a qualitative variable. And if you recall, just like from last week or previous weeks, um, a qualitative variable, we need to make sure that we consider the different levels of that variable. So how many levels of qualitative predictor are there for education? So this line here tells you that. So education has 3 levels. 1 equals high school, 2 equals college, 3 equals postgraduate. So there are 3 levels, hence we will need 2 dummy variables in the regression equation. So this step is pretty much the same as before. But what is different this week is the general form of the regression model. Okay, so you've so far been working with a linear function um, for modeling quantitative variables. So if you recall, the quantitative response variable was always a linear function of the predictors, right? Well, this week it changes. This week we have predictors that are expressed in an equation that uses, well, it's an exponential equation, right? So you can see clearly here we're using exponents, and here are the predictors. So if you notice that um, this part here is pretty much linear, right? It's just like how you would have expressed a multiple regression model for a quantitative variable last week. And similarly, you have the same case here. The only difference again is this is an exponential function. Okay. So once you run your the R method to get the estimates for regression, you will pretty much plug them in right there, and that will be um, your regression equation. Um, I do want to discuss this th- this regression model, the general form of the regression model, and why it is this way. So for that, I will switch to Zybook and just quickly talk about why this function is as it is here. So this is the section that talks about um, logistic regression. This is section 6.1, and here we have the logistic regression function given. So if you notice here, we're just using one predictor, beta 1x. Okay, so that's why you just have one predictor given here, and this is general form of the logistic function when you have one predictor. Okay, so now let's look at this plot here. So this figure 6.1.3 is a logistic function for Hall of Fame based on career hits. So the x-axis here shows the number of hits, number of career hits, and y-axis is the probability that the player was inducted into the Hall of Fame. Okay, and um, what we expect here. So you can see clearly we have a zero, first of all. Well, probability ranges from 0 to 1. So we have the 0 line here, and we have the 1 line here. So Hall of Fame equals 1 means that the player is inducted into the Hall of Fame, and 0 means the player is not. Okay, so the logistic regression function, when you plot, looks like this red curve here. Okay, so it will have values that range from 0 to 1. Well, that's why the response variable takes values from 0 to 1. And it's important to note that on the y-axis, because we have the probability, so any point on this curve here for the y-axis represents the probability that the player is inducted into Hall of Fame. So, for example, if you notice this question here, it says the logistic model estimate of the probability a player with 3,000 hits is in the Hall of Fame is what? So we have 3,000 hits, so that's approximately here. If we go up on this line and on the curve, so we must have a value between 0.75 and 1. And out of the three choices, zero point 0.9 is the most appropriate. So this is the probability that the player is in the Hall of Fame if that player has hit 3,000 or has had 3,000 hits. That's what that means. So this is what, on a very high level, logistic regression represents. You will get values from 0 to 1 for each prediction, and that prediction is basically the probability that your response variable takes a value of 1. So if, for example, the probability that the response variable equals 1 is 0.25, well, that's kind of low probability. So you would think that um, for that case, the expected value of y or the response variable should be 0. But if the probability comes out to be zero point 0.9, like in this example, then that means the response variable should take a value of 1. And so you can kind of see that we will get probabilities in the range of 0 to 1. And there will be a point where we will say, okay, at this point, anything above a particular probability level, like a threshold, we will say that y should be 1. And you can kind of control that in your programs, but we will keep things simple, and anything more than 50% will be considered y equals 1. Anything less than 50% is y equals 0. So getting back to step 2, so in this model now, we have one quantitative predictor and one qualitative predictor that has 3 levels. So it must use 2 dummy variables. So altogether, there should be 3 terms, 3 predictor terms in the model. So that's why we see x1, x2, x3. And then they have their respective beta, this, this, the slope coefficients. And we also have beta 0. And this is the logistic function. Okay. Now, you don't have to derive this, but this can be converted to a function like that. And um, the nice thing about this function here is that this is expressed in in a linear equation, right? So this part here is what you are most familiar with that we have been doing so far, and just that the left side is slightly different. So the left side uses the natural log function now, right? So that's a result of rearranging this equation um, and getting rid of the the exponents here. And when you do the conversion, you're left with this equation. Okay, and this side of this equation is the natural log of odds. Okay, and I'm sure you've heard of what odds are, and this is exactly what that is. And if you read it here, the left side of the equation is the natural log of odds. So what we can do now is when we have our beta estimates here, after running the R function, we'll get our beta estimates and we will plug them in here. And then we can plug in values for x1, x2, x3 and get our prediction. The prediction will not be the exact value of y. The prediction will be the log, the natural log of odds of, in this case, default being equal to 1. Okay, so what are the odds that default equals to 1? So we're going to get natural log of odds. Okay, that would be our prediction. So this is slightly preferred over this. Well, first, because I think it's simpler to understand. The right-hand side here is a linear equation. And also, I think that everyone is sort of aware of what odds are. So the only difference now here is to express the answer here would be expressed in natural log of odds. Okay, but either of these is okay. So when you get your beta estimates from the output, you can either plug them here or here and get to your equation. Okay, so let's run this. So this is the part that will run the logistic regression, and it uses the function GLM in R. Okay, the function is set up in a very similar way like before. So we have default, tilde, and then the two predictors, and R will create the dummy variables by itself. And then you'll have to remember to set family equals to binomial. Okay, that's using a binomial distribution. Okay, so once you run this, you get your output, and then you run summary of the output, and you get um, the summary output that looks very similar to what you've seen before. So it has those estimates, and um, so here are here's the credit utilize variable, the quantitative variables, and then these two are the dummies for education. And the estimates are given here, and then we have, instead of the um, the t-test, we have the z-test now. Okay, so this is the z value and the p value. Okay, which would be similarly interpreted. So using this, we would get our estimates. We can plug them in either of these equations. Okay, I would probably prefer this one, and that is expressed here. So we will take these outputs, take these estimates, plug them here in this. This is the standard form of the logistic regression model. And then this is the form of the model where it's expressed in natural log of odds. Okay. And once you have this, the next step then would be to do the interpretation for beta estimates. So let's now interpret our betas. And this is very similar to before with some changes, of course, because we now have log of odds equal to the linear function of the predictor terms. So we're going to look at the credit utilization first. Okay, so as you know, credit utilization was between 0 and 100%. So you can be anywhere between 0 and 100%. And the data that was given to us was in decimal points. So for example, 0.40 meant that credit utilization is 40%. So the estimated coefficient for variable credit utilization is plus 34.3869. So this means that on average, the change in log odds uh, for defaulting, so log odds for defaulting, is 0.3438 for each percentage increase in credit utilization, holding all other variables constant. Now, you may ask me, why is this 0.3438 and not 34.38? Well, that's because imagine if x1 increased by 1 For credit utilization, that would mean an increase of 100%, right? Going from 0 to 1 would be going from 0% to 100%. But what we want is the change in log odds for each percentage increase, so 1% increase, right? So basically we take this value and we're going to divide it by 100. Now you don't have to do this each time um, for every predictor because not all predictors will be expressed in terms of percentage. But when the predictor is expressed in terms of percentage, where a 1 unit increase means 100% increase, then you do have to make this conversion. So for example, let's just imagine that x2 was a quantitative um, predictor, okay, and the coefficient, um, the beta coefficient estimate here is minus 1.4975, right? So then we would do the interpretation and say that x2 was not, um, percentage. It was just numbers. So then the interpretation would be simple. It would just be that log of odds would decrease by 1.4975 for each unit increase in x2. Just like before, very simple, the only difference being log odds. Well, here we have a situation where x1 predictor is quantitative but expressed in terms of percentage. And therefore, we have to consider 1% increase, um, not a 1 unit increase, which would be 100%. Okay, so I hope this is clear. And all you do is you take this and you divide it by 100. So now that you have 0.3438, um, and that is going to be the change in log of odds is going to be plus 0.3438 for each percentage increase in x1. Okay, or each percentage increase in credit utilization gives you a change of 0.343869 in the log of odds. Okay. Now, there's another way you can express this because we don't want to deal with log of odds. We may want to express this in terms of just the odds. And to do that, you can calculate the um, this exponent of 0.343869 minus 1. Okay. If you do this calculation for any um, for any betas here, if you do this calculation, for example, in this case, it gives you 0.4104. And what we have done now is we've expressed this in terms of odds. So this is plus 0.4104. What this means is that the odds of defaulting increase by 41.04% for each percentage increase in credit utilization, holding all other variables constant. Okay, so this is slightly better because we're more used to dealing with odds as opposed to log of odds. Okay, so we get when you do this calculation, you get plus 0.4104, and so the odds of defaulting increase by 41.04% for each percentage increase in credit utilization, holding all other variables constant. And again, this figure is obtained by dividing 34.38 by 100 because credit utilization is expressed as percentage. And this is obtained by multiplying the decimal value 0.4104 by 100 to turn the decimal into a percentage. So 0.4104 is essentially 41.04%. And then note that the sign for this is positive. If this was a negative 0.4104, then the odds of defaulting would decrease by 41.04% for each percentage increase in credit utilization. Okay, so it's pretty simple, and um, I think the only challenging part of this interpretation is the fact that this x1 predictor um, is expressed in terms of percentage. So now let me talk a little bit about, let's say that we go back to the example that let's just assume that x2 was a quantitative predictor, okay? And the beta estimate for this is minus 1.4975. And so we can now calculate the same, we can do the same steps and do the interpretation for that beta estimate. So for example, if it's minus 1.4975, we would say that for each unit increase in x2, log of odds would decrease by 1.4975 units. That would be very simple. Okay. We can also calculate this for um, for that, right? For we can calculate this part for this beta estimate. So let's do that. So we have minus 1.4975. So if I take minus 0.417 or 1.4975. So the this exponent part here would be calculated using this formula, exp. Okay, exp of this, the value in cell B1, which is minus 1.4975, is 0.223689. And then when you subtract 1 from it, you get minus 0.77631. So now this is very simple. We will say that the odds of defaulting decrease by 77.6% for each unit increase in x2. Very simple. Okay. Now we note here that these two terms were dummy variables, right, um, for education. And we said that this would be college and postgraduate, would be 2 and 3. So for college, now we go back to the real scenario, which is that this is a qualitative, this is a dummy variable for a qualitative predictor. And therefore, X2 represents college education. So when you have someone with a college education, then relative to a person with non-college education, you would have log odds decreasing by 1.4975 units. Okay, and similarly, we can express that here in terms of this. So for a college educated individual, your odds would decrease by 77.6%. Okay, so it's very similar to how we have been doing the interpretation, just slightly different because now we're dealing with either log of odds or odds. But if you just follow these steps, and in most cases, you will not have to deal with percentage predictors, so you won't have to take your beta and divide it by 100. You'll just be able to do the interpretation. So next, we can also calculate confidence intervals for the slope parameters. These are for the slope estimates for the predictor terms in logistic regression. And these can be calculated with um, conf, confint.default with the level, whatever level you want to pick, 90% or 95%. And the input is the model that is saved in logit. This is from the previous step. So that's that. And once we run it, we can print, and I'm rounding here to four decimal places. So you get your confidence interval. This is for the intercept, and then your predictor terms in the model. This is um, the lower, the lower value, and then the upper value for the confidence interval. So, and the interpretation for these would be very similar to how you've been doing in the previous weeks. In step 4, we will do an overall test for the significance of the model. So if you remember in multiple regression models previously, when we use quantitative response variable, we were relying on an overall F-test, which was based on the F distribution. And the null hypothesis was that all of the betas uh, are 0. the beta parameters, the um, slope coefficients for the predictors are zero, and the alternative was that at least one of them is non-zero, right? Well, in the case of logistic regression, we have a slightly different test, but the process is exactly the same. This test is called Hosmer-Lemshow goodness of fit test, and this is based on the chi-square distribution. So if you're not familiar with chi-square distribution, I encourage you um, to search for it and read a little bit about what the distribution looks like. The idea is very much the same. You have a distribution, and we're going to get a test statistic and a p-value, and we will compare that p-value against the level of significance and then reach a conclusion. Now, because we are dealing with a goodness of fit test, the null and the alternative hypothesis in this case are going to be slightly different than what you're familiar with. The null hypothesis in this case is that the model that you just generated fits the data that was used to generate it. Okay, and the alternative is that the model does not fit the data. So it's a fairly simple hypothesis. If you reject the null hypothesis, then clearly you're going to conclude that the model does not fit the data. If you fail to reject the null hypothesis, you will conclude that the model fits the data. Okay, so this test, Haslem.test, is the function in R that runs it, and this is in resource selection library. This is the library that we installed in step one, and now we're calling it, and then we're calling the function that is here. And once we get this, once we get the output, you will see that the test statistic this time is not an F stat. It's called X squared, or this is chi-square. This is really chi-square. That's what they mean there, is 31.582. We have the degrees of freedom that comes with a chi-square distribution, and we have the p-value. Okay, that is the p-value that you're going to compare against the level of significance. So in this case, the p-value is 0.9676. We will compare it with, say, level of significance of 5%. Clearly, the p-value is greater than 5%, so we failed to reject the null hypothesis, and that means that the model indeed fits the data. So this test is also explained in section 6.4 of the book, so right here. So I encourage you to read this so you get a better understanding of how the test works and also the distribution that it relies on. So next we move on to the confusion matrix. So this is a way to test the utility of the logistic regression model. Using the confusion matrix, we can figure whether the model does a good job of predicting the response variable on the dataset that it was trained with. Okay, so it's kind of like we're taking the dataset that the model was trained with and putting it in to for the model to be able to do predictions, and then we compare the predicted value of the response variable with what was input into um, into the model when it was learned. And so we're comparing predictions with actual response variable. Okay. Now, because the response variable is binary, it's 0 or 1, so it is often called a label. Okay, so it's a label whether it can be 0 or 1. So the actual labels are from the data set, and then the predictions are from the model. And so the idea is that we get this 2 by 2 matrix where the prediction can either be 0 or 1, and each row here you can have the actual label being 0 or actual being 1. The first cell represents the true negatives, okay? Because this cell here will include counts of how many in the data set, how many of the actuals that were 0 are actually predicted as 0. So these are true negatives. Okay, the prediction is correct, and that's why we call it true, and then negative because it's we have a 0 here. Okay. Similarly, we can also have well, clearly the model is not just going to give you 100% accuracy. So you can have cases where the actual labels are 0, but the model predicts it as a 1. When that happens, we have a false positive. Okay, it's positive because prediction says it's a 1, but it's false because the actual data points were 0. So this cell here will include counts of how many false positives we have. Okay. Similarly, we have false negatives. That's where the prediction says it's 0, but the actual labels are 1. So this cell will contain the number of false negatives. And then we have true positives. That's when the actual label is 1 and prediction is 1. So what we will get then is a 2 by 2 matrix with counts, the number of um, true negatives, false negatives, and true positives. And of course, for a good model, we would want the true negatives and the true positives to be high in number. So we want all of the labels that are 0 to be predicted as 0, and all of the labels that are 1 to be predicted as 1. And we don't want too many false positives and false negatives. Okay. Now, once we get these numbers, we can calculate. And by the way, these are the definition of true positive, true negative, false positive, and false negative. So once we have these counts, we can then calculate the accuracy, the precision, and the recall. Okay. The accuracy is the ratio of number of correct predictions to the total number of observations. So this is all of these three metrics are expressed here in terms of these true positive, true negative, false positive, and false negative. So you can calculate the accuracy like that, the precision like that, and then the recall like that. Okay. And we will use these three metrics to see how good of a job the model does. And so you can calculate that using this code here. So we take the two predictors, we create a subset, okay, and we do our predictions. Um, and the prediction is on the model that was just trained. And the new data, remember in the previous weeks, we used to create this new data, right? We used to create a row of data to input into the model. Well, this time we're just taking all of the all of the data all of the data set, variable education and utilize, and inputting that into the model so that we get predictions um, for all of the rows in the data set. Okay, so and if the prediction so clearly the model will predict the probability, right? The output will be um, a probability score. And so what we then can do is we can create a decision variable where we can say if the probability is more than 50%, then we can say that that's a label of 1. Okay. And otherwise, so in terms of this problem, it would mean that um, the the person being uh, the person defaulting on the credit is true. That's a 1. If the prediction of the probability is less than zero point 0.5, then we will say that's a 0. Okay, so 0 means no credit default. So that's what we would do, and then we would use this row here to create a table. Okay, this is we're stepping now towards creating the confusion matrix. So this table here, what it does is it takes the actual, these are the actuals, these are the labels, credit default, dollar sign, and then the default, that's the response variable. And we would then take the predictions that were calculated here and we would put it here. And then these two are input to the function table. So this would create a table just like the confusion matrix. And we can then label the columns and the rows like that. Okay, so this would be the 0, 1, and the 0, 1. And in the next step, we would then, for the row, we would um, paste the actual. That would be the name of the rows, because in the rows, you're going to have, just like the confusion matrix shows you here, the rows represent the actual data points, and the columns represent the predictions. So basically, we've just created the confusion matrix that's shown above, and here's the output. Okay, so you can clearly see that we're getting a pretty good model here. For the true negatives, we have 254, the true positives are 303, and the false positives and the false negatives are, the counts are fairly low. So this is good. And using this, now that you have these scores, you can then calculate the accuracy, precision, and the recall. So all you have to do is figure where's the true positive. So the true positive is here. Where's the true negative? That's here. You take these numbers like that, and it's explained very well here, and you can plug them into these formulas to calculate your accuracy, precision, and recall. And then you'll use those to discuss, how good of a model do you have. Clearly, we want, um, we would want the accuracy to be high, precision to be high. So these metrics can be used to also study, in addition to the significance of the model, these metrics can be used to study the utility of the model, how good of a job the model is doing. So you'll be expected to do that in the problem set. Okay, so I think this is fairly simple. There is a little bit of code involved, but you'll be able to use this code as is with just changing the data set, the data frame names and the variable names um, for your problem set and the project. So next we're going to calculate the area under the curve for the ROC curve. And this is a very popular measure to evaluate the utility of a logistic regression model to see how good of a job the model is doing in distinguishing the two different classes of a binary response variable. Okay, so basically, like, how good of a job it does to predict zeros as zeros and ones as ones, or no's as no's and yeses as yeses. Okay, that's essentially what this is. It's a measure that will tell you, um, how good of a job your model does as predicting zeros as zeros and ones and ones. Now, you will get a plot like that where the y-axis is going to be true positive rate. And using the confusion matrix, you can calculate the true positive rate um, for different thresholds. Okay, for different thresholds on the y-axis, and true positive rate is defined as true positive divided by true positive plus false negative. So the denominator is true positive plus false negative. The numerator is true positive. And then on the x-axis, you have false positive rate. And the false positive rate is essentially just the false positives divided by the false positives plus the true negatives. And this can also be calculated for different thresholds on the x-axis for false positive rate using this equation I just mentioned. Okay, so we can plot all these dots here, and then we can create the curve, and it will look like something like that. And then we can calculate this shaded area under the curve, and it will always be between 0 and 1. And ideally, we want this area under the curve to be as high as possible. So the ideal situation in which the model predicts zeros as zeros and ones as ones without any misclassification is one where the green curve will become almost like a step function. It will go up on the y-axis and then become parallel to the x-axis. So that would be the most ideal case, but that almost never happens in the real world. So you always have this kind of a curve that you get. And so this is the example I just gave, where you have a perfect scenario. The area under the curve in this case is 1, and you have this true negative and true positive for the different thresholds, okay, of the output that you get, right? So the threshold it varies from 0 to 1, and you can use these different thresholds to calculate your true negatives and true positives. And in this case, these two curves will not intersect. And so you have a perfect situation where you're predicting the positives as positives and negatives as negatives. But you'll get a curve that looks mostly like that. Okay, so it'll be like that. In this case, the area under the curve is zero point 0.7. And you can see that for different levels of threshold, you have some misclassifications going on, right? So you have some false negatives, okay, and false positives. So there are some predictions that are not true. And when that happens, you can, again, using these different thresholds, you can create this plot. And when you do that, and for the case where you don't have 100% accuracy rate, you're gonna see a plot that looks like that. Okay, and this is much more common. And so we can then calculate the area under the curve, like in this case is zero point 0.7. And of course, we will do this using R, so it will output the area under the curve and the curve. It will plot the curve as well. This is the worst case scenario. So this is where we just have false positives and false negatives. Area under the curve is zero point 0.5. So the model has no discrimination capacity to distinguish between positive and negative classes. Okay. And in this case, this is a really weird case. You're probably never gonna see this, but in this case, you have basically a model that predicts zeros as one and ones as zeros. Okay, so it's kind of like pretty much the worst case scenario, but you're almost never going to see that. You will always have somewhat of a curve as long as you've built the model well, you'll have a curve that looks like that. And so the two things we're looking for a curve like that, and we want the area under the curve to be as high as possible. So if you have two models predicting the same response variable, and in one case you have a higher area under the curve, well, that's one way to say that that model is doing a better job. So now getting back to step 6 here, where we have to calculate the area under the curve and create the curve. This code here will do that. So we're going to use this PROC library. We get our true labels. These are the actual zeros and ones for credit default, and our predictions using the model for those, okay? And those you can get using the model variable $sign and fitted values. We um, we can enter the labels tilde predictions in ROC function and get our ROC. That's pretty much the curve itself. And then we can use the AUC function and the input will be the ROC here and round the answer to 4 decimal places. Okay, and then we can plot the ROC. So that's how simple this is. So we get our curve, we get the area under the curve. So when we run it, we get something like that. So first of all, see, this model actually is doing pretty good. It's almost, you, you can see that this is almost like a step function that I was talking about, but then you do have some curvature here. And then this becomes parallel to x-axis, okay? So we can see that the area under the curve is 0.9859. That's a pretty good model in predicting zeros and ones. So this is essentially what this is. So you have to get that plot, you have to explain exactly what is going on here. Make sure to mention the true positive rate and the false positive rate on the x-axis and how it's created using the different thresholds. So the thresholds are from 0 to 1 and then here 0 to 1. Okay, so these are different thresholds that we're using to calculate our true positives and false positives. Sorry, true positive rate and false positive rate. And we're going to get this curve. This line is the worst case scenario. So it also prints the sort of like the worst case scenario line. So you can get a feel for, um, how good of a curve you have relative to the worst case scenario. And then you get your area under the curve. And that is pretty much the analysis um, for the ROC curve. So make sure to do this analysis in words um, for your assignment, and make sure to explain how the ROC curve is generated. Okay, that's very important to understand how it's generated, and then explain the higher value of area under the curve and how that can be used to see how good of a model we have. So next we can do predictions using the logistic regression model that we just created. Now remember that the model predicts the probability of y equals 1. So in this example, it predicts the probability of defaulting on credit. So meaning that the variable default equals 1. That is what we're defining as defaulting on credit. The code section below predicts the probability of defaulting for an individual who is a high school graduate and has 40% credit utilization, and another individual who is a postgraduate and has 35% credit utilization. So the credit utilization here is not drastically different, but education is. So let's see what the predictions are going to be. So just like before, we create one row, a data frame of one row where education is 1 and credit utilizes 0.40 for 40%. So that the education is 1 because that is what we defined high school education as. Okay, and then we use the predict function. The first input is the model, second is the data frame that we just created of one row, and then the type we're going to set to response. We can set this to class, and the output will then be a label. So the prediction will be a label. But we're setting the type to response because we would like to see a numeric answer. So we want to see the probability and the probability that the model outputs. So here you can see that for the first prediction, we get 0.9927. So that is almost, the label is 1. And um, because 0.9927 is almost 1. So clearly, um, for someone who has high school education alone and is utilizing credit at 40% level, there is a pretty high likelihood that they will default on credit. And similarly, we can do another prediction with education is 3 for postgraduate, and the credit utilization is 0.35. So we set the type to response again because we want a numeric answer, and we get 0.2559. And so that is less than zero point 0.5 clearly and much lower than 0.9927. So the prediction here for the label would be a, a 0, okay, or um, that the likelihood is that the individual is not going to default on credit. Okay, so just this prediction works very similar to how it was before. We've only added this type equals response so that you can see your probabilities. Otherwise, you can always use type equals class, and then the prediction here and here would be labels, either 1 or 0. So this pretty much concludes the lecture this week. I hope this will help you um, participate in the discussion as well as finish the problem set for the week.